Good morning and welcome everyone. I am AshayAswale, a PhD candidate at Worcester Polytechnic Institute, working with Professor Carlo Penciaroli. Today, I'm thrilled to share with you a research on heterogeneous coalition formation and scheduling with multi-skilled robots. Picture this scenario. We are embarking on a series of experiments with one primary goal, completing all these experiments in minimum amount of required time. These experiments, let's call them tasks, each demand a unique combination of sensors and tools. To simplify, we'll collectively term these sensors and tool combinations as skills. Now, a research question takes shape. How can you complete all the tasks that require specific skills when multi-skilled robots have cross-schedule dependencies? Let's dive deeper into a research problem. We imagine having fewer robots than the tasks. The challenge is clear. We can't simply assign one robot to each task and call it a day. Our robots are versatile. They possess multiple skills concurrently. Take for instance the robot in this image where it wields both the execution arm and a resource sensor simultaneously. However, not one robot can have all the skills needed for any task. This leads to coalition formation where multiple robots must collaborate to complete a task. But here's a twist. All robots in a coalition must be present simultaneously. For instance, in the same excavation task, it demands both arm and a hauler bucket. This coalition constraint implies that any schedule change for one robot ripples through the entire coalition. This results in several cross-schedule dependencies that we must address. To further complicate matters, we must account for the stochastic nature of the robot's travel times, ensuring that schedules must remain robust even in the face of potential delays. In our research, we present two possible solutions to tackle this challenge. First, we employ a solver based on mixed integer linear programming or MILP. MILP is a mathematical optimization and feasibility program. This method involves formalizing the problem and its necessary constraints and then utilizing readily available MILP solvers to produce the solution. We also introduce a more agile alternative, the greedy solver. This approach begins by selecting the most effective robot and task pair, and then it systematically evaluates all the other robots to identify the best partner robot for the task. This process continues iteratively until all the tasks are completed. In our experiments, we initiate with multiple robots positioned near the center of the workspace as indicated by these green icons. Each robot possesses a distinct skill denoted by either a circle or a cross. The tasks are represented by blue icons, accompanied by the symbols indicating their specific skill requirements. Our solvers provide a comprehensive solution which includes the path that each robot must traverse, illustrated by these black lines. Upon completing their assigned tasks, the robots return to the central depot, completing the operation cycle. To assess the performance of both approaches, we evaluate their relative performance. When it comes to solution quality or cost, we calculate the ratio of solution cost from the greedy solver to that of MILP-based solver. Here we see that MILP solver always produces better solution. However, even for scenarios involving substantial 8 skills, the greedy solver consistently achieves solution within a margin of just 1.6 times the MILP solution. But when we shift our focus to wall clock solving time or WCST, the efficiency of greedy method truly shines. In the graph shown here, we depict the logarithmic ratio of WCST. Notably, as we scale up to more complex scenarios, the greedy solver outpaces the MILP-based solver by an astonishing margin, where greedy solver is over 5 orders of magnitude faster. In summary, our research introduces two distinct approaches to address the coalition formation and scheduling challenge. The MILP solver excels in delivering slow but very good quality solutions. The greedy solver offers rapid solutions, albeit with suboptimal results. In future, We will work on enhancing the greedy solver by implementing more advanced heuristics. Additionally, we also plan to decentralize the system to improve the parallelism. Thank you everyone.